lab this afternoon. We'll meet downstairs. Next week we're doing double E2 elimination. And the handout I just passed out was about elimination. We'll be using the dibromide next week that you made 6 weeks ago. It should be in your drawer. That'll be your starting material. Dibromide has 2 bromines, potential leaving groups. Mass spec. Substitution. 2 mechanisms, SN1 and SN2. The shaken not stirred is a formal report, is that right? I remember. Okay, that'll be due next week when you come to lab. Reactions of how do you make oxygen a better leaving group? Protonated. Make it positive, then it's more willing to leave. What's another way to make an OH group a better leaving group? Convert it to a tosylate. Yes, we showed that. Tosylate is actually isolated. It becomes a brand new compound. You can fully characterize it, the melting point, etc. Then you can turn around and react it with some type of nucleophile. If it does SN2, if this undergoes SN2, don't we expect inversion? Because how does the nucleophile come in? Backside. If the leaving group is forward, the nucleophile comes in from the back. That's why this is now dashed. Okay, so that should be pretty straightforward. Let's look at this here, though. This is how you make the tosylate. React with tosyl chloride and pyridine. Pyridine, which is a weak base. Tosyl chloride is where you just have the chlorine with the tosyl. Okay, that's generic. But the tosyl would be benzene ring of the methyl, which is a toluene. I'm not going to show mechanism here because ultimately here, you need to know structure. This is oxygen bonding to the SO2, right? Oxygen bonding to the SO2. It's a substitution reaction here. The oxygen replaces the chlorine. We make this plus what? What's the fate of the H and the Cl? It's going to produce ACl. ACl is an acid. Okay? Pyridine is a weak base to consume the acid. We're going to go through this mechanism. We'll go through it in organic 2. It's a substitution, but it's not SN1 or SN2. Because, I'll give you a little preview, if these electrons were to attack here, you're not going to just kick off the chlorine, which would be SN2. Why? Because when you come in here and you add to the sulfur, something's got to break or move away from the sulfur. What's more likely to move away, the sigma bond to chlorine or the pi bond to oxygen? It turns out it's the pi bond to oxygen because the pi bond is not as strong. Pi bond is not held as tightly between there. When this comes in, actually what happens is the pi bond moves up onto oxygen. How does that ultimately lead to the chlorine being displaced? Well, it's a different mechanism. It's going to be a mechanism more like organic 2 chemistry. Okay? But what you need to know right now is keep this in mind. Whenever you add here, the weakest bond is going to break. The sigma bond is not the weakest bond. In this case, the pi bond is weaker. And that's the one that would break away from the sulfur. That's the main point there. You can see this in your textbook. It may show you more. I'll cover this in organic 2 when we cover the chemistry of alcohols. And by the way, a lot of what we're doing will be repeated in organic 2, but I'll say boom, boom, boom. Remember this from organic 1? Okay. Now, importantly, whenever you make the tosylate, you do no chemistry at the carbon. No chemistry there. So the stereochemistry of that carbon does not change. That should hopefully make sense. But over here, when you do your substitution, now we're doing chemistry at the carbon. And if you do SN2, it's backside attack. And with SN2, we get inversion, right? We look at this transition state, how you get inversion. So, does that make sense? Just a two-step process, the steric chemistry. Okay, so we looked at oxygen being a leaving group. What about nitrogen? After oxygen, can it be a leaving group? Well, yes. Nitrogen can be a good leaving group. But like oxygen, only if you give it a positive charge. A neutral nitrogen is not typically going to leave. Now, giving nitrogen a positive charge is actually sort of rare. It leaving is actually rare. But I do show it because it should be analogous to the oxygen. Here's an example. If you take this dimethyl aniline and react it with HI, the outcome is actually the monomethyl aniline plus methyl ida. Now what's happened here? How can we describe this reaction? What happened? We removed an alkyl group from the nitrogen. So here we have two alkyl groups there, we only have one. So it's a dealkylation of a tertiary amine, that is a tertiary amine. It's actually an aniline, but an aniline is a type of amine, right? So that's what we're doing with HI. Now it's just a secondary amine or aniline. Now this actually has a name, Herzig-Meyer, and it's not a common reaction. You thought they just sold furniture over on Wrightsboro Road, but actually it's a reaction here. Okay, mechanism for this. What do you propose we do first? Show a complete mechanism for this. First step, anybody? Suggest as the first step. Yeah.
Kick one of the methyls off, and then just
Okay. What do you mean kick one off?
like ionize one off.
Ionize a methyl. Just a carbon leaving?
Yeah.
Okay. What would that give?
A positively charged carbocation, which like the methyl.
It wouldn't give a positively charged carbocation. What would be positive? The methyl would then be positive?
Oh no, the nitrogen would be negatively charged.
You want to move it. You want to move these two electrons onto the methyl to give. There's the methyl bonded, but if you move the electrons onto the methyl, it becomes a lone pair, and that's actually a minus. And we get there's a lone pair there, and what else is here?
Nothing.
Nothing. These electrons are no longer bonded. So you're saying it ionizes away. What's the charge of the nitrogen?
Plus.
Positive. Okay. Problem is, this is not good. You're not just going to make carbanions. Why will a halogen just go away and become minus? Why when you put HBr in water does it become H plus and Br minus?
Iron.
Because the halide is very electronegative. It loves to be minus. Carbon doesn't love to be minus. We can form them, but no. For example, if you put methane in water, is methane an acid? No, it doesn't do that. Also, this nitrogen doesn't have an octet. What have we said about oxygen, nitrogen, and not having an octet? It's not good. Don't do that. No.
Where do the electrons?
Now, question. Let's move to this. What would you then do next if this happened? How would you then get the product? And let's see another problem with this.
Well, now that I'm thinking about it, the hydrogen isn't going to go anywhere near the nitrogen. Because that's positively charged.
You got H plus. You want an H bonded here?
Yeah, that's not going to happen.
You got a plus and a plus bonding together. As we learned in way early on, pluses don't like pluses, they like minuses. Okay? So now you have issues here. Okay. As described up here, though, we do want the nitrogen to become positively charged, but it's analogous to the oxygen. This is an acid. We can show this as H plus and I minus. Here's a take home. Anytime you have a mechanism under acidic conditions, usually the first thing you want to do is do an acid-base reaction. Use the acid. Won't care, we can protonate. Maybe a question about that. I'm just going to draw that as phenyl. I'm going to draw these CH3 methyls out, okay? Protonate. Now that nitrogen is positive, just like that one. The difference is this one has an octet. 2, 4, 6, 8. Protonate oxygen, make it a better leaving group. Here we protonate nitrogen, make it a better leaving group. I suspect you haven't recognized that nitrogen is the leaving group here. Now what can we do? Methyl iodide. This needs to bond to what? One of the methyls. How can we do it? Does it have a leaving group on it? Does that carbon have a leaving group?
No.
Positive nitrogen. These electrons can then attack the carbon, kick off the positive nitrogen, and what does that give? Gives the product shown. Iodine makes bond to methyl, make methyl iodide. Nitrogen is leaving. See here, it's kind of reversed. The leaving group is actually the big old thing, and the methyl was actually the carbon we attacked. And, okay, it's just like protonating the alcohol and alcohol leaving. So there's an example. Hopefully, you see it's very consistent with what we did above. Any questions about that? Do you see it now? Any questions? That's an odd reaction. I'm probably the only organic extractor in the state of Georgia that covers that. But what I want you to see is the consistency. Okay? Because a main thing of what we're getting at here is when you leave this course, I want you to be able to see new things and to be able to understand them, rationalize them on your own. But importantly, you guys seem to be afraid to use your knowledge on new problems. Don't be afraid to use your knowledge. Consistency. Question?
For the SN2 reaction, say more often than with the larger group is going to be the leading group in this case, or is it just
No.
it's just how it kind of works out?
No, the positive atom is the leading group. That's all we can say here.
Okay. And it doesn't matter which method it's at.
Doesn't matter which method. Now, are you going to attack over here? I mean, that was protonated. You're going to attack there and kick the nitrogen off of there, have the iodine bonded there? No, why not? Because that's not a tetrahedral carbon. You don't do SN1 or SN2 at a non-tetrahedral carbon. These are tetrahedral carbon mechanisms. Why? Because if the iodine did attack there, which bond would break? The sigma bond to nitrogen or the pi bond to carbon? Pi bond to carbon. That's why you don't do SN2 there, because you would not just directly kick off the leaving group. Okay? Anytime you have a pi bond to your atom, you're not going to be doing SN1 or SN2. Please see the consistencies. Sulfur. Can sulfur be a leaving group? Yes. Actually, your body uses sulfur as a leaving group in lots of biochemical processes. For example, your body makes epinephrine. Or in England, they call it what? I believe. Adrenaline. Is that right? Am I right? I think I'm right. I think about it. I think it's called adrenaline, okay? We call it epinephrine because we don't like combinations. How do you make epinephrine? You make it from norepinephrine. I'll tell you what the nor means in a minute. What's the difference in the two? That has a methyl on the nitrogen. So that's a primary amine, that's a secondary amine. How do we get the methyl? How does your body put the methyl on? It uses this guy, SAM. S-adenosine methionine, I'd have to think about it. You can look it up on Wikipedia. You can buy it at Whole Foods or wherever. It's used as a supplement. What is it? It actually has a sulfur here, if you can see it on your paper. It's a positive sulfur with a methyl. This nucleophile attacks the methyl and kicks off what? Kicks off the positive sulfur as a leaving group. Now this sulfur is not protonated. It's not an H that made it positive. It's positive because it's bonded to 3 carbons. You can look at it. How many lone pairs are on that sulfur? Okay? Well, you should be able to tell that. For it to be a positive charge, there has to be 1 lone pair there. Okay? So you can digest the structure. Well, what mechanism did I just show? SN2. Nucleophile attacking, kicking this off. Now, importantly, this guy has 2 H's, but this only has 1. Because after this puts on the methyl, I'm just showing the end here, this is positive now. All right? To get to this, we have to lose an H to go neutral. So with a neutral amine, you actually have to lose an H to go neutral. Well, this can happen next. I mean, there's got to be a minus here, or even water. If something can take this, I'll use water to take it. You can consider it equilibrium, but something has to take the H, leave these electrons behind, and then you get that with the lone pair. So when you use amines as nucleophiles, you do have to have then remove the H afterwards to go neutral. Okay, or some type of base. Okay, we'll see more examples. The main thing here is the body uses this to supply a methyl group, an electrophilic methyl group. Positive sulfur being a leaving group. Positive oxygen can leave, positive nitrogen can leave, positive sulfur can leave. Is this the only nucleophile in norepinephrine? And we have lone pairs over here. Why is it that the nitrogen attacks and not the oxygen? This goes back to acid base. What do you know about nitrogen versus oxygen? The lone pair activity. Oxygen is more electronegative. Oxygen holds its lone pairs tighter, right? Nitrogen's a worse parent. It lets its lone pairs get out there and do backside attack. Yeah? It's just like the acid-base discussion. The amine is more nucleophilic. Oxygen's a better parent. Keeps its kids in the house. All right? What's noramine? Usually when you see nor, that means it implies it's missing something. What is this missing compared to that over there?
Method.
Yeah, it's missing the method. So a lot of times that's where maybe this was discovered first and had a name. And when this was sort of discovered, they said, well, it's missing the methyl, we'll call it norepinephrine. A lot of times you'll see nor. That means it's missing something compared to that. or noradrenaline. I think the English call it noradrenaline. Okay? A couple of applications of this. There's plenty of applications. Let's just see a couple. What we're talking about. You ever heard of mustard gases? Very toxic, dangerous. Used as chemical warfare, nasty stuff. Right here. This is a sulfur mustard gas. It's yellowish, that's why they call it mustard. Why is it so reactive? Shown below. What happens is, now this is not directly related to the reaction we just saw, but it's related to what we've seen over the past lecture or lecture and a half. What happens is, this becomes activated because these electrons attack here and kick that off. Now that is a three-membered ring. Actually, I should have drawn it this way. Okay, it's the same thing. If you draw it this way, that off, then you see how you make that bond right here. And now the sulfur is bonded to the second carbon. Sulfur bonded to the second carbon. But this is very easy. Why is that so easy? Even though it's a three-membered ring. What makes that easy? John?
It's an intermolecular reaction.
Yeah, it's intermolecular. It's like boom. Just make boom, kick you off. Intermolecular reactions are often easier. That's favorable. Yes, it's making a three-membered ring, but it's like boom. Two different molecules, I have to go way over here before I can do backside attack. So this is set up to just boom, kick it off, and it happens to be easy. But now when you create this, what type of, you have a carbon with a sulfur. And the sulfur has a positive charge, potential leaving group. And because it's a three-membered ring, it actually would like to open back up because it's strained. And that makes you wonder, well, why did it form in the first place? Well, it does, because it's internal. But now it's very reactive, sulfur leaving group. Now some of your biomolecules, which have like amino groups, they can act as nucleophiles and come in here and keep that sulfur off. And now your biomolecule is covalently attached to this N carbon. Now you could say, hey, well, why doesn't this just attack here and kick off the chlorine? I mean, that could just kick here and kick that off. But so could here. You kick here and kick it off. The problem is, this is way much more reactive than this. Why is this so much more reactive? Because it get that three-membered ring formed. Or something like this is not going to form a three-membered ring. You just have to come in here and do your standard on SN2. Very reactive, and once all your biomolecules start reacting, you're going to be in trouble. Okay? In your lungs and everywhere. You also produce HCl, which causes a lot of problems if you start producing a lot of that in your lungs. So it's a double whammy. Sometimes these things can be used for benefit. For example, nitrogen mustards are actually used to treat cancer in a lot of cases. Chlorambucil is used to treat leukemia. It's this structure here. What happens first is these electrons come in here, and you get a three-membered ring with nitrogen being positive. Then the biomolecule attacks, and you have your biomolecule attached to the carbon, and you've now alkylated your biomolecule. The nitrogen now has an alkyl group, but this can be used to treat cancer. The problem is they're not that selective. The only way you get selectivity here is if the cancer cells take this up preferentially over the normal cells. Because if your normal cells take this up, they're going to get alkylated. So these things, while they can be effective, they don't tend to be highly selective. But some cases they can be, apparently against leukemia. Okay. But there's going to be side effects. It's going to make your hair fall out probably because it'll do this in your hair cells and kill your hair cells. So there's lack of selectivity here. We can go talk about that in a bit, but you can look at that. Those are some examples. Have you ever talked about nitrogen mustards in biology course? Do you think? Okay. All right. We're down to G. That makes me wonder what goes before G. F, A, B, C, E, F. What was F? What were we just doing? Looking at various leaving groups, right? What were we doing? Okay, G. Gee whiz. Now let's look at nucleophiles. Let's focus in on them. And again, we're focusing on SN2 right now. What type of nucleophile is best for SN2? We'll clarify that a little bit later, but typically you want a strong one. You want a good nucleophile. Okay, how do we judge good nucleophiles? A couple of different ways. First, your anions are typically more nucleophilic than the neutral counterpart. Here, both of these oxygens can be nucleophiles. The anion is going to be more nucleophilic. It has higher electron density. Okay? I mean, if we come in here, if we want to attack this carbon, right? The nucleophile is going to attack the carbon. Why would it attack it? Well, we have a dipole here, and that's partial plus, partial minus. The nucleophile can come in here. We can do this. Why would this be attracted to partial plus? We're assuming this is going to have some partial negative character. Well, electrons are negative. The more negative this is, the more it's going to be attracted to your partial plus carbon. You come in here and do the backside attack. Well, which oxygen is more negative? Duh. It's that one, right? Anions are more nucleophilic. Over here. Which one's more nucleophilic? Ammonia or the anion? The anion, right? Importantly, though, they both can be nucleophiles. This is weaker. Now, when these act as nucleophiles, they're going to have to lose an H to go back to neutral, just like that amine reaction we did. We'll see more examples of that. Okay, next thing. A less electronegative atom has the more reactive lone pair. Now, a lot of this will coincide with our acid-base discussion. Which is a better nucleophile, ammonia or water? I've already given you the answer. Now, they're both neutral, so you can't say one's neutral and one's an anion. Here we're dealing with different. Here we have oxygen, here we have nitrogen. The ammonia is going to be your better nucleophile. And we explained 15 minutes ago why. What?
Electrons aren't color split.
Jack?
The electrons aren't color split. Nitrogen's not as electronegative.
Right. Nitrogen doesn't hold the electrons as tight because nitrogen's not as electronegative. Oxygen holds them tight. It's a better parent. Nitrogen is the less electronegative atom. It thus has the more reactive lone pair. It's a worse parent. Let its lone pairs get out there and do reactions more easily. So that's an example of the same row. What about the same group? Which is more nucleophilic, H2S or H2O? Well, which is more electronegative? Oxygen or sulfur? Oxygen, more electronegative, holds its electrons tighter. Sulfur is not as good a parent compared to oxygen. Less electronegative, electrons are more out there and being able to attract to the partial positive. A neutral sulfur is a better nucleophile than a neutral oxygen. And your body actually uses sulfur not only as a leaving group, but it also uses it as a nucleophile. Which is a better nucleophile, I minus or F minus? Oh, they're both anions. Well, the answer's here. I minus. Why? Less electronegative. It doesn't hold the electrons as tight. Now, which is more stable? Which is more stable? I minus is also more stable because it's bigger, and because we're dealing with an anion here. And some students are like, well, why is the more stable anion more reactive? Well, that could be a kind of discrepancy. It actually is. Because the main thing here is the electrons aren't held as tight. There's some other more advanced arguments there, but okay. Steric effects. We talked about steric effects around the carbon of the leaving group, and the more substitution and more sterics here, the more difficult the SN2 is. And actually, if you have a tertiary carbon, you don't do SN2 because it's so bad and slow. But what about sterics with a nucleophile? It's the same thing. If your nucleophile becomes too bulky around the lone pair site, it's not going to be able to get in here and attack. Look at this. Primary amines are more nucleophilic than secondary, and they're more nucleophilic than tertiary. Got lone pairs all over the place. But if this lone pair is going to come in and do backside, you've got these wings on here. Okay? Like if I'm a lone pair and I'm going to do a backside attack, I can just approach and come in. What if I have ethyl groups all around me in a tetrahedral manner? Well, I can't get there with my method, you know? Maybe I can come in this way. That'll have to be very precise, and it's a less chance of that happening. So it's going to be slower. Okay? Or consider if I was going to bring in a plane and land it right here. If I got big wings, I'm going to clip all these trees. If I get rid of the wings, I can slide right in. Okay? The more substitution, it's going to make your nucleophile less nucleophilic, less reactive. So the sterics affect not only the nucleophile, or not only the carbon in the leaving group here. Sterics is important for both of these guys. Actually, tertiary amines are often called non-nucleophilic. They're so sterically hindered that a lot of times they won't do SN2. These are actually good for E2 reactions. We'll see that a little bit later. Because a lot of time when you do elimination reactions, the substitution reaction can be a competitive outcome. If you don't want the substitution to occur, you use a sterically hindered base, which is not going to do substitution well. We'll see that a little bit later. Now the substitution there, it was on the nucleophilic atom, on the nitrogen. Down here, it's not on the oxygen. Each oxygen only has one substituent, but it's next to it. The carbon that's bonded to the nucleophile has alkyl substituents. This one only has two, this one only has one. And so the substitution over here can also affect it. This is a better nucleophile than this guy. And again, this is often used for elimination reactions because it doesn't do substitution that well because of the crowding. Not on the atom, but next door to the atom. Now, there's a difference between nucleophile and base. We need to make sure we recognize that. A lot of this coincides with our base strengths, but sometimes it doesn't. For example, this is the better nucleophile, but which of those three is the better base? This is actually the better base because there's more donation towards that oxygen. Okay? But it's the worst nucleophile. Why? Because when you talk about nucleophile, you have to come in here very precisely from the backside attack. And because this has to be very precisely, sterics are important when you do this. When you act as a base, the H is real small. And when you attack the H, what type of orbital are you attacking?
S.
It's just an S orbital. An S orbital is spherical. And when you attack a spherical orbital, there's no such thing as backside. You attack it from any direction. When you attack an H, it's not a precise attack. And the H is so small, because of these two factors, sterics does not usually matter in an acid-base reaction. But sterics is very important when we do method substitution at like the tetrahedral carbon. So this is a stronger base because it's more electron rich. This is a stronger nucleophile because it has less sterics. What's the difference between a base and a nucleophile? When it attacks an H, it's called a base. When it attacks like a carbon and kicks off a leaving group, it's called a nucleophile. Let's take a look at that. Any questions, please ask. Okay, what's another effect that can be important in judging nucleophilic strength? Resonance. This is an isolated anion. There's no resonance delocalization. But here we have resonance delocalization. We can delocalize the charge onto oxygen. So this is a full minus. Does this oxygen have a full minus? What's the charge?
Partial
It's only partial minus, because we know it's delocalized. So which is going to be attracted more to this partial positive? A full minus or a partial minus? Full minus. Now that coincides with base strength. This is also a stronger base. Does that mean that this can't be a nucleophile? Actually can still be, but it's not as strong as that. Okay, over here. That lone pair is sitting right there on that nitrogen. There's no resonance. But what about this? Is that lone pair sitting right on the nitrogen, or is it delocalized by resonance? We've already done the resonance structures of that. Actually, if you look back at your resonance structures and you look at the hybrid, this nitrogen actually has some partial positive charge. And why would a partial positive be attracted to a partial positive? It's not. Well, it depends on how much. Certainly, it's just not as reactive as this, because this is a full lone pair, okay? Lone pair is resonance delocalized. So if your lone pair is delocalized or spread out, it's going to make it less reactive. Hybridization effect. This nitrogen is going to be more nucleophilic than this one. They have the same kind of substitution, like 2 carbons, 2 carbons. They're both neutral. They're both nitrogen, so what's the difference? The difference is this lone pair is in what type of orbital? sp3, where this one is in what type of orbital?
That's me too.
In what?
SP2.
sp2. Okay? So what's the difference in the lone pairs in terms of reactivity? Or their structural... Is one held tighter to the nucleus?
Yeah,
sp2 is held tighter to the nucleus. It's 33% S. It's only, okay? This coincides with base strength. This is a stronger base. It's also a stronger nucleophile. In essence, that nitrogen is a better parent than this nitrogen. Okay? It's a hybridization effect. The majority of this does coincide with acid-base that we looked at 2 months ago. There are some differences, for example, up there with those oxygens, because sterics is very important. Question?
Did you also argue resonance on this one?
Well, the lone pair is not involved in resonance. The lone pair is not in a p orbital. Resonance is only with electrons in p orbitals. You have resonance here, and you can show the pi bonds there, but that doesn't influence the lone pair. The lone pair is in a hybrid. We're up here. What type of orbital is that lone pair in?
P.
P? Was any time a lone pair is next to a p orbital, a lone pair is going to want to be in a p orbital? If it wasn't in a p orbital, we wouldn't be able to talk about resonance. That lone pair is in a p orbital. And typically, we'll say that lone pairs in p orbitals are just not reactive. Although there is a couple of exceptions to that. But that's a good rule to start with. This lone pair is delocalized. It's busy doing resonance stuff. Okay, let's see if we can do this. For each group, for each series, put them in order of nucleophilic strength, from weakest to strongest. So number 1, well, label these 1, 2, 3, 4. And 1 would be the weakest, and then 4 would be your strongest. Why don't you want to all do the first series first? Okay. Everybody do the first series. Weakest to strongest. If I rewrote that, I'd probably rewrite it to strongest to weakest. Because I would be looking at the strongest. That's the thing I'd look at first. Once you identify the strongest, call it number 4. these four, which is the strongest nucleophile? Tur? First one? Okay. I'm not sure yet, but explain your argument. Why?
Oxygen holds electrons.
Okay.
Is less
All the other ones are oxygen nucleophiles, right? Sodium hydroxide, charge. What is this? Let's forget about the spectator ion. That's O minus. Forget about that. It's O minus. It's a neutral. This is S minus. Okay? So why is this stronger than that? Tor? You're saying?
I was saying that sulfur is less electronegative than oxygen.
Right. They're both anions, so that's not your answer. The difference is oxygen holds it tighter because it's more electronegative. Sulfur doesn't hold the lone pair. It's got 3. Doesn't hold them as tight. Yeah. So this is stronger than that. Is it stronger than that? It's the same thing. It's an oxygen. It should be. Both anions. Is it stronger than this? Well, yeah. Not only is that an oxygen, it's also neutral. And we know that anions are stronger. Yeah, this is your strongest, so that's 4. Let's move over here. Of these 3 that are remaining, which are all oxygen, which one's the strongest? OH. What is this? AC. Acetate, right? Water. Well, at this point, we can also maybe ask this. Which one of these 3 is the weakest?
Water.
Yeah, so let's call that 1, because we're weakest to strongest. Neutral. Okay, these. Which one is the strongest? This one, what?
It's not resonance.
Because the other one is resonance delocalized. You've got to recognize your resonance, okay? This is just like when we showed up above. So it should be
3.
like this. Weakest, strongest. Actually, that way back. Yeah.
Could you also say something about the size of the OAC? Because it's a really bulky nucleophile, technically.
Yeah, it's a little bulky.
In comparison.
But to me, the resonance is more of a huger, more important consideration. Okay, down here, do these on your own, and we'll put them in order on Monday. Let's see where we're at. Please look ahead, summing it up. Then we'll move on to sort of example SN2 reactions. Some of them will have like names. Okay, we'll do examples. Then we'll move to SN1 a little bit. And then we might get to the elimination handout on Monday. Perhaps near the end on Monday. Have a good day, guys. See some of you this afternoon.